Hello, calculus scholars. In this video, we'll go over some key ideas about particle motion and go through some particle motion problems. I'm not going to read through all of the key facts on this page, but you should. You should review total distance, how to write an equation for position. You should know that in order for speed to be increasing, both the velocity and acceleration have to have the same sign, how to recognize particles moving left, right, etc. For average value and average rate, I don't think we need all of the detail or explanation that's below here, but you should know both of these equations. Okay, so let's go to the next page. Again, this has some key facts to review, but also key words to look for in word problems, like initially, at rest, at the origin, etc. Total distance is here, and we know that it's the integral from A to B of the absolute value of velocity. And we also added a note here about maximum velocity. In a problem, if it asks you about what a maximum velocity is on an interval, you want to be thinking about relative or absolute maxes on the velocity equation or graph. Or we also know that those occur when the graph changes from increasing to decreasing. That's where relative max occurs, right? Increasing to decreasing. Or you might want to use the extreme value theorem. A quick reminder about the EVT. If you are trying to find a maximum value for velocity, you can take acceleration and set it equal to 0 to find the critical points. We know critical points are indicators of possible relative mins and maxes. So if you found all of those critical points, you can then make a table. So let's say we had critical points at 0, 2, 4, and my endpoint is 5. So I'd have my endpoints, and then I'd have my critical points here in the middle. And you can plug it in and get a value. So let's say that this is 10, negative 5, 15, and 4. Well, then it's clear that the maximum velocity is here at 15 because we found all of the critical points, which represent the relative maxes, where maxes could be, and we've got the endpoints, which can also be maximum values. So that's one way to go about finding the maximum velocity. Okay, so next we have a multi-part word problem, which is really common on the free response to have something like this. You should pause the video at this point. You should try to do the entire problem, and then you should start the video again and watch me go through how I'm solving it and the explanation to make sure you know how to do all of this. Okay, so at this point I'm assuming you've done the problem. We're going to go to part A. Use the data in the table to estimate the velocity of the airplane at takeoff. That is, estimate the value of the limit of v of t as t approaches 20 from the left. So if we're approaching 20 from the left, that means we're looking at time here. We are going closer and closer and closer to 20. At the same time, we want to look at what the velocity is and what it's approaching. So here, as we get closer and closer to 20 for time, our velocity is getting closer and closer to 95. So for A, the limit as t, not x, as t approaches 20 from the left, of v of t is 95. Okay, now let's go on to B. Use the data in the table to estimate the value of v prime of 6. So v prime of 6, remember the derivative of velocity is acceleration. So really we're being asked to find the acceleration at t equals 6. Now t equals 6 is not actually in the table, so we have to estimate it. And the way we estimate it is by finding the average rate here. So what we're going to do is look at the x values that fall to the left and the right of 6. So it's 4 and 10, and then we're going to use those y values as well. So we're going to set this up to be v of 10 minus v of 4 over 10 minus 4. This formula gives you the average rate of change. So it's an average or an estimate of the derivative. So again, acceleration is the derivative of velocity. So we are finding the derivative or an average approximation of it by using the average rate of change formula or finding the slope. Okay, so now we just plug these values in. V of 10 is 75. V of 4 is 50 over 10 minus 4, which is 6. So this is 25 divided by 6. Now, going back to the problem, it says use correct units and interpret the meaning of the value in the context of the problem. Now, as a reminder, let's go back and look. Our velocity is in meters per second. So if we were doing a position function, the units here would be meters. Velocity is position divided by time, so it's meters per second. When we go to acceleration, we are doing velocity over time. So we're doing meters per second, which is the same thing as meters per second squared. So that's always true for acceleration. You're always going to go from some linear unit like meters to meters over a time unit to your distance or linear unit over time squared for acceleration. Okay, so in this problem, they asked us to actually explain the meaning. So I'm going to clear the page here so that we can have room to explain. So we're talking about B, and we just talked about the answer here being 25 over 6 meters per second squared. So that's using correct units, but now it's asking us to interpret the meaning of the value in the context of the problem. So we can say that at around or at t equals 6 seconds. So at t equals 6 seconds, the velocity is changing, and we know it's actually increasing because acceleration is positive. So the velocity is increasing at a rate of 25 over 6 meters per second squared. Okay, so again, we can take a look at our velocity. Our velocity has increased, and at t equals 6, it's approximately, I should say, it's increasing at a rate of approximately, because we found an average, right? We are approximating 25 over 6 meters per second squared. So here you would probably get a point for finding the value, and then 1 for your explanation with the correct units. Okay, so now let's go on to C. Approximate the value of the definite integral from 0 to 15 of v of t dt using a Riemann sum. So we're going to be using rectangles, and it's a right Riemann sum, and we have 3 subintervals. And then we have to explain the meaning. So remember, this is something that we should automatically know. The area under a velocity curve gives us displacement. If, make that an N, displacement. If there had been an absolute value sign here, instead of displacement, it would have found distance traveled. So we'll just keep that in mind for when we're going to our meaning of the definite integral. Okay, so no absolute value here. We're actually going to calculate v of t. All right, so it said 3 subintervals. We're going from 0 to 15. So we can see the table gives us an interval from 0 to 4, an interval from 4 to 10, an interval from 4 to 15. It said we were going to use a right Riemann sum, so that means we're going to be using these 3 values and not 0. Now remember, Riemann sums essentially give us rectangles, so we're finding areas. So we're going to want to do base times height. Our base is the interval. So here, how big are these intervals? Well, here the interval is 4, here it's 6, and here it's 5. So those are our different bases. And then the height is the v or y value. These are our height values. Okay, so our first rectangle has a base of 4, and then it's being multiplied by 50. Then we add a base of 6 times a height of 75. Then we add a base of 5 times a height of 87. And then you just either do that mentally or you plug it into a calculator. These numbers are big enough that you are probably going to plug this into a calculator. And we get 1,085. Okay, so now that we've found that, we're supposed to use correct units and explain the meaning in the context of the problem. Well, we said that the integral of velocity, the area under the curve, gives us the displacement. So what are we talking about here? We're talking about the displacement of an airplane as it takes off along a straight runway. So we can say from t equals 0 to t equals 15, or in the first 15 seconds, the plane's displacement, or net change in position, is approximately 1,085 meters off the ground. So we included units, the value that we found, the actual integral's value, and we're explaining that it's the plane taking off the ground and its displacement specifically off the ground. Okay, so that's part C. All right, let's clear that and then we'll do part D. All right, part D. Suppose the velocity of a second airplane can be modeled by f of t. Using this model, find the acceleration of the plane at the time it reaches a velocity of 55 meters per second. That's the stall speed. So what's its acceleration when it might stall out? So this is our velocity equation. So I'm just going to call this v of t. I know they've called it f of t. Actually, yeah, let's change this to f. But we'll just write that this is velocity of the second plane. Okay, so they want to know, when does this velocity equal 58? And then we need to find the acceleration at that time. Now, is this something that you're going to be able to do by hand? Definitely not. You should have a graphing calculator, and you should graph this. Okay, so plugging this into your calculator, and then as y1, and then plug 58 in as y2. You might have to play around with the window a little bit. I used a window of 0 to 20 for x and 0 to 150 on y, and a scale of 2 and 25. And I got a graph that looks like this. And then 58 comes in about here. So we can use second trace, intersect to find this point, and it is approximately 5.782. Now, this is a value that should be saved as a letter on your calculator. So I'm going to store this as A. As a reminder, you do that by going to your home screen and typing X, store, so the stow button, and typing A. Okay, so now that I know when the second plane reaches a velocity of 58, and now I can find the acceleration of the plane at that time. Okay, let's delete this, or erase this graph so there's room to find the derivative. So we already said acceleration is the derivative. So I'm going to find a of t, and it's the same as f prime of t. My coefficient is going to stay. The derivative of the natural log is 1 over whatever the value is inside. But we have to use chain rule and then also multiply by 2t plus 1. Okay, so a of t equals 15.7 times 2t plus 1 over t squared plus t plus 1. And now we want to find a of capital A, which was approximately 5.782. So we're going to plug that value in, and when we do that, we get approximately 4.905. Let me rewrite that so we can see. Approximately 4.905. Use the correct units. It's meters per second squared. Okay, so that problem had two parts. Figuring out when the velocity is 58 meters per second, and then finding that time and using it to plug into acceleration. All right, for the next problem, there'll be a second video.